as promised, the integral of ln of x dx. It's deceivingly simple upon first glance, and then you realize I have no clue how to solve it upon first summing across it. And that's a good normal reaction to have, because we're supposed to have two functions here. Integration by parts requires we have some u of x, some v of x, right? And that's how we're allowed to apply the rule in the first place. We only have one function here, right? ln of x. No. This is where I think integration by parts really shines. It's that you can't say that there's one function, because there's always a 1, right? You can always put a 1 there if you want to. So what we can do is we'll go ahead and set u equal to ln of x. Right? Obviously, we're not going to set it equal to I, because we'll just be in a loop. Right? So our dv is actually set to 1 dx, or just just 1, right? Let's see what happens. Differentiate, we get 1 over x. Integrate, we get x. Now, I can go ahead and perform this again. I could integrate this one more. I could differentiate this one more. But really, that trick of, you multiply the diagonals together, and then at the very last row, you multiply the row. You can do that at any time if you like. So, because this is supposed to be the integral of v du, as we saw in the first video. So we can go ahead and stop here. We can multiply these two, and we get x ln of x minus the integral of x over x dx. And would you look at that? The integral of dx is x, and we get a final solution of ln of x minus x. You must and should preferably, if you take integration b seriously and solving integrals seriously, is committing this integral to memory, because it shows up a lot. Especially, you were solving a much more difficult problem, and within the difficult problem, we have to know the integral of ln of x for some odd reason. And if we don't, we're frozen, and our opponent won. Everybody should know that the integral of ln of x is this by heart. So let's go ahead and quickly go back to the previous problem just for fun and see how we would go about solving that one with this knowledge. Okay, back to problem 3. So prior to solving problem 3, the intuition we had based upon the first couple problems that I presented to you is, well, x to the third eventually differentiates to 0. So let me make that equal to u, and we saw the problem arose that end up having to know what the integral of ln of x is. But now we do know. We figured it out, and let's see what happens when we take this route. So we'll just integrate once, nothing crazy, right? X ln x minus x. Uh, and this one just becomes 3x squared. We get the plus, minus, and follow the procedure. This looks a little tricky. It's okay. We'll go step by step. We have x to the fourth ln x minus x to the fourth. And then this is going to be, the product of these two is what we're integrating. So what I'm just going to do is I'm going to add a plus instead of the minus out in the front. And the integrand is just going to be distributing this term into this binomial. So we just get a integral of negative 3x cubed ln x plus 3x cubed, right? Plus 3x cubed dx. And you may already be regretting choosing this route, but don't fear too much, because look what we have here. That's just the integral we started with. We have minus 3i over here, and this integral is pretty trivial, so let's just go ahead and simplify and solve for I. So I equals x to the fourth ln of x minus 1, right? This becomes a minus 3i. This becomes x to the fourth 3/4. We add I on both sides. So plus 3i. We get a 4i, divide by 4, and the final solution is 3/16. Right. So it's not too bad. That wasn't that terrible. I'm sure, you know, the setting our u equal to ln of x is much easier, much quicker. But yeah, that was pretty fun. Just it's very important that you know the integral of ln of x, because it's going to show up here and there, and the last thing you want is to be stumped. So yeah, take care. Before I go, there is something about this problem that is very, very worth pointing out. Is look at this solution compared to the previous one, and let's say I was masochistic and I kept the limits. Let's go ahead and evaluate this with these limits and see if we arrive at the same solution. It's a good way to check yourself too, but let's see which one is easier in your opinion. So we have x to the fourth ln of x minus 1. We have this over here evaluated from 1 to 2. So when we plug in 2, we get 16/4 is 4. So we get 4 ln 2 minus 1 plus, look at that, we get plus 3. Then we subtract the little round. Let's say we have 1/4 ln of 1 minus 1 plus 3/16. It's already looking a lot simpler than the previous one, unless you're just no amount of arithmetic can stump you. If so, you know, Godspeed. But if you're someone like me who has a weakness in arithmetic, um, this alternative, what initially looked like very tedious, actually ended up making the calculations for the definite integral much faster than uh, how we initially solved the problem 3. So let's go ahead and just confirm that they're the same. So we have 4 ln of 2 minus 4 plus 3 is minus 1 minus, well, ln of 1 is 0, so this becomes a negative 1 over 4. This becomes a positive 3 over 16. And we distribute negative. This becomes a plus. This becomes a minus. This is the same thing as 4 minus 4 sixteenths minus 3 sixteenths. That's 1 16th. And look, would you look at that? We get our final answer, 4 ln 2 minus 15 16th. It's pretty beautiful, right? So I don't expect you to look at an integral like this and be like, wow, if I would have set, you know, the integration to ln, the arithmetic is going to be a hell of a lot easier. I don't expect you to have built that vision, to see that visualization in your head. But it is important to know, and I think it's really fun to see just how different the solution is by one simple change. Not how different the solution is, but the path to the solution is just by that small change that we made. So, yeah.